Welcome to this video. In this video we're going to see what there's called the full range and half range expansion. So what are these? Also known as the full range Fourier series, cosine Fourier series, and sine Fourier series. We will see. Now the idea here is that I have a function f of t. And f of t is not necessarily periodic. I have a function, imagine this one, f of t, that is whatever you want all around, okay? And now we think, okay, that function, I want to represent it with a Fourier series. But I know that Fourier series only work for periodic functions. But you say, well, I don't care, because I just want the function in the interval ab. For example, the x I pick a equals to 0 and b here, so this interval. I want to represent the function here as a Fourier series. I don't care what happens out there, right? And then you see outside of that interval, and then you say, okay, fine. So I can make the function periodic. If I get this, and I repeat it periodically in whatever way I want, then I know I will have a Fourier series that will represent the function here very well. Now, how do I make the function periodic in order to fit that it's got a Fourier series representation? There are three ways, well, there's an infinite number of ways, but there are three ways that are really important that we learn. One is called the periodic extension, one is called the even extension. The even extension is going to be associated with the cosine Fourier series, okay? So you can call it even Fourier representation or cosine Fourier series, we will see in a little bit. And the odd extension is going to be called the sine Fourier series, and we're going to see why. Okay, so imagine that the function that I want to represent is this one. We're going to do several. But we're going to plot, first plotting what are the extensions of these functions that are what we call the periodic one, what we call the even one, and what we call the odd one. And we're going to analyze their periods. Let's begin with the periodic extension in black here. The periodic extension is pretty simple. I get the function from a to b, which is something like, so let's just plot this here to try to make it as similar as possible to the plot within my drawing skills. So the function is something like that, in that interval, right? Something like this. So how do I do the periodic extension? Well, just take the function and make periodic copies from that interval. Now from here to here, I'm gonna get this. You see, I make copies. These are identical copies, all of them. My drawing skills are limited, right? But you get the message, right? It's basically take periodic copies. Hold on. Take periodic copies. Take many copies of this and do and extend them periodically both sides of the interval, like here and there, right? And then here. And there, all right. So you see, this is the periodic extension of the function. Now you can tell that the period is b minus a. Okay? So the period of the function is the same length as the interval for the periodic extension. And now I can do a Fourier series. This is a periodic function. I will do a Fourier series of this periodic function. And in this interval, it will reproduce exactly the full function in this interval. Not here, because it's doing something else, but I don't care, right? Because what I care is the interval a to b. So for a to b, that would work, and that will give me a periodic extension of which I can do a Fourier series. All right. How about the even extension? How does that work? Well, I would get in the interval ab, the key point is that in the interval ab, the function has to be the same, because otherwise it would not reproduce what I want to reproduce, right? So I would get the function is something like this. Right, same as before, from a to b. What I do is that I want an even function. What does that mean? Well, remember that imagine this is the axis of symmetry. So the function has to be equal at both sides of the axis of symmetry. So if you want to do an even extension, it's like an even function, right? You need to do the same on the other side. You see, on the left of the interval should be the same curve. It's just my drawing skills, right? So use your imagination to compensate for my drawing skills. It should be the same. All right, so you take the function and take it here, and on the other side of the axis of symmetry, they have to be equal. You see, when I move 1, I get this value. It has to be equal to the value when I move 1 in the other direction. They have to be equal 1 to 1, okay? So this is the periodic, the even extension. Let me just try to draw it better. The even extension is prolonging this in an even symmetry on both sides, okay? Now, and then when I've done the even extension, what I do is I extend it. I draw it again, the even extension. So what is it? It's even, right? So I need to get all this thing here. On both sides of, this is a new axis of symmetry, on both sides of the axis of symmetry has to be even. Well, you can just get this and copy it again, or just do the even extension of this again, which is, right, has to be like that. And then, again, a copy that has to be even. You see, this is, again, the same thing, the same copy as this. And then, same goes here, it has to be even. So, this one would go like that. Okay? So that's the even extension. And as you can tell, this thing, the period of that is twice b minus a. Because the period is this. And then extend this, right? You see how you do it? Every time you get an axis of symmetry, you do an even extension. What does that mean to be even? It means that whatever the value is here has to be the same at the other side of the axis of symmetry. Always. Every time you have one of the axes of symmetry, values have to be the same at both sides of it. So if you were continuing here, it would go like that, right? And then at both sides of the axis of symmetry, at both sides, always the same value. All right, so this function is obviously different from this one, right? This one is actually, doesn't have a parity, a defined parity, and this one is even. That's nice for integration purposes, as you know, right? We can actually take shortcuts when we do that. This one is going to be called as well, the Fourier series that comes out of this is going to be called the cosine Fourier representation. Also called the even Fourier representation, once we do it. This is just the extension of the function. When we do the series, it's the cosine Fourier series, because it's going to contain only cosines. Because the cosine is even and the sign is off. So if it's an even extension, it will contain only cosines. And we will see when we compute it, right? Now, the even extension, as you can tell, is a different function than the periodic extension, the regular periodic extension. But still, the Fourier series will reproduce exactly the function from A to B. Outside of it, they will be different, all of them, but inside A and B, the three functions will coincide. The one that gives me the Fourier cosine series, the one that gives me the full range Fourier series, and the original functions. Okay? All right. What about the odd extension? How do we do the odd extension? Well, the odd extension, as you may have imagined, is from A to B is exactly the same. So let's just draw it. Yeah, drawing skills going down. Okay, like that. It's exactly the same as all the others. From A to B, they all have to coincide because our objective is to write Fourier series that represent this function from A to B. Remember, we cannot do the Fourier series for this function because this is not periodic. So we are building auxiliary functions, capital F, capital G, capital H, that they coincide with the function you want the series of in the interval you're interested in, but they are periodic. And there are different ways of making them periodic. Right, so from A to B is the same. What I need to do now is the odd extension. Instead of doing the even one, that is the same value on both sides, now I need the negative value on the other side. If this one is this value, on the other side it would be minus that value. Let me just draw the axis here, the axis of symmetry. Right, and then if it starts here, then this is the same length more or less. The same, in this amount should be negative, this amount. So it should go to here. So you get a function like this. You see, it's the negative of this one. This is a mirror image, if you want, to these points. So the symmetry is odd to it. Again, this is more like a rotational symmetry, this one a parity inversion symmetry. Okay? So this one is taking this, but draw it negative, like that. Okay, the same point in here. So at the same distance, this one and this one have to be equal in magnitude, but opposite in sign. And now that you have that, well, just extend it. Same as before. Just extend it. So here it will be this one again. So we go like that. And here we go this one again. So like that. And here we go this one again. So like that. All right. And then same on this side, right? So here, again, it has to be odd. So that goes all the way up here. And then goes to this negative one, same as here, same height should be. And then here, goes again, like that, and so on. That is the odd extension. What is the period of this one? Again, this is what repeats, you see? This one repeats, this one repeats. So the period is, again, same as for the even extension, is twice b minus a. So the period of the periodic extension is smaller than the period of the odd and the even extensions. This one will yield the sine Fourier representation. All right. Sorry about this. Fourier representation. Okay. So these are three ways. Again, let me emphasize that the three of them coincide with the function f of t from a to b, and they are different elsewhere. Okay, and all these three functions that are different to each other, are different from f. They all coincide from a to b. So all the Fourier series that we will obtain for that one, for that one, and for that one will yield exactly the same value between a and b. So the three are valid. Three different ways of representing the same function. Let's do an example of this. So let's consider a function, and let's do the three representations, and let's compute the three Fourier series for that. All right? So we'll begin with the periodic one, then we'll do the even one, then the odd one. Okay, let's do it. All right, here's an example. Find the full range, sine and cosine Fourier series representations of the function f of t equals t in the interval 0 to 4. So I want to represent t as an infinite sums of sines and cosines that nails it in the interval from 0 to 4. And I have several ways of doing it. Now, the function is this one. It's just a straight line with a slope of 1, right? And the first thing that we're going to do, we're going to compute the full range expansion. Full range expansions could contain sines and cosines. May not contain some or may not contain others, depending on the characteristic of the function, but in general will contain both. All right, to do the full range expansion, the first thing that we need to do is the periodic extension of the function f of t equals t. Now remember, the periodic extension is take the interval 0 to 4. Let me just draw here the axis. Minus 4, minus 8, minus 12. All right. So the function is, minus 4 is not the same. Minus 4, minus 8, minus 12, something like that to make it a little bit better. Okay. So we take this interval, and the function in this interval is this one. So what we do to do the periodic extension is the simplest of them all. Just draw it again, and draw it again, and draw it again, and draw it again. But do it right, and so on and so forth, right? So is the function all the same, done several times periodically, just transported periodically to the right. Okay, that's the periodic extension. So this is the periodic function of which we need to find the Fourier series. This thing we call it capital F of t. Remember, capital F of t is the periodic extension of small f of t. Okay. All right, so let's find, so first of all, what is the period? The period is 4. T is equal 4. What would be omega? Well, omega is 2 pi divided by t, right? So it's 2 pi divided by 4, and that means that it's pi over 2. Okay? All right, so for the full range expansion, first thing that we need to do, okay, let's write the Fourier series. The Fourier series is, let me just write, capital F of t would be equal to a0 divided by 2 plus sum n equals 1 to infinity an cosine of n omega t plus sum n equals 1 to infinity bn sine of n omega t. And then let me write the expressions for an and bn. En is 2 over t integral, and we take some t0 and t0 plus capital T of the function f of t cosine of n omega t dt, and bn it's equal to 2 over the period integral from t0 t0 plus t, f of t, sine n omega t dt, where t0 we pick, whatever is the best for computing. If I start here, I get all this area from 0 to 4, but if I start a little bit here, I get this area. If this is t0, I get this area, but also I end here. So what is missing, I get it here, right? So it doesn't really matter where I start doing the integral, because it's periodic. All right, so let's compute first t0 alone. A0 alone. A0 is 2 divided by 4, which is the period here. Integral, and let's get t0 equals 0. That's the easiest one, from 0 to 4. Let's do it. So 0 to 4. And then we get f of t, which is t times the cosine, but the cosine of 0, so it's 1. So t dt. Right, so this thing is 1 over 2. And then here you get 1 over 2 t squared from 0 to 4. I'm not going to be doing this in all the integrals because we know what this thing is. So we get, what do we get here? Is 1 over 4 and then 4 squared, which is 16 minus 0, right? So this is 4. A0 is 4. Okay, I'm not going to be doing all the steps for all the integrals. And we get A0 equals 4. Okay, so we collected. Let's have it, maybe I'll collect it where here. A0 is 4. All right, wonderful. So you see, if it were a sine expansion, A0 should be 0, because it would be an odd function, and all the cosine, and A0 counts as a cosine coefficient, should be 0. So we have one cosine coefficient here, at least. Let's compute an. An for n is larger than 0. Okay, this thing is 2 over 4. Then the integral, let me separate this a bit. The integral from 0 to 4 of t cosine of n, then omega. What is omega? Omega is pi over 2. So n pi over 2 t dt. So this integral is easy. It's an integration by parts, and you can do it. The result of this integral is actually 0. It's easy to check that it's actually 0. All right. In any case, do it by parts, and it's really simple by parts. I'm just not gonna be doing all the integrals because it will take forever, and t times cosine is something that you know how to do. All right, so yeah, all the cosine coefficients larger than 0 are 0, but A0 is not 0. Okay? All right. Exercise. Do it by parts, find a general expression, and then do it taking the limits when n goes to 0. Okay? Because this expression, the expression that you get at the end, is only 0 if n is different from 0. In the limit with 0, you should get an indetermination that when you solve it with a limit, gives you 4. So the next one that we do is the bn's. So the bn, I'm going to do it here. So by the way, let me just write here, an larger than 0 is 0. Now the bn is again 2 over 4 integral 0 to 4 t sine of n pi divided by 2t dt. All right. So this thing you can do by parts as well, and it's a very simple integral. And what you get is is minus 4 over n pi when you do this integral by parts. We'll do plenty of exercises as well later on, so I wouldn't worry too much, but this integral by parts is again something that you should be able to solve. All right, so that means I collect the bn's here. Bn it's equal to minus 4 divided by n pi. All right, so that means that capital F of t, which is the periodic extension of f of t equals t, it's equal to 4 divided by 2, right? So 2, then minus 4 over pi. I take the common factors of the b's outside, the minus 4 over pi, and then sum n equals 1 to infinity of 1 over n sine of n pi over 2 t. And that is the full range expansion, or the full range representation. There are many names. Let's call it full range expansion, full range Fourier expansion, full range Fourier representation of f of t in t in the interval 0 to 4. All right. Hopefully not too difficult. These integrals are very easy. They're by parts integrals, okay? All right, let's do the even extension, so the cosine representation. All right, so let's do the even extension now, which is gonna be the cosine Fourier series. Now we know that this one will not have, in fact, I could remove this one outright, but let's not, and let's compute it and see that it's indeed 0. But you know, I mean, maybe if you're like short of time computing something, you know that the even extension should only contain cosine terms, the a0 and the ans. They cannot contain the ends because, again, an odd function, so an even function, which is the even extension, cannot contain odd elements like the sine. It has to be cosines, which are the even functions. So you could cross it out from the beginning, but let's not, and let's give it just a sanity check. The first thing that we need to do to compute the even extension, the cosine series representation, is to compute the even extension of the function. Remember, so the function is f of t equals t. So what we get is that from 0 to 4 is the same function, f of t equals t. But now we need the even extension, so I need to extend to the other side of the axis of symmetry, getting the same value at both sides. So this would be this one, the, mirror with respect to the axis, okay? Like that. So that at the same distance from the axis, the value is the same, all right? And then, of course, you keep going like that. Right? And the same here. All right, so that's the even extension. That's a periodic function. There's the function that we call g of t, which again coincides from 0 to 4 with f of t equals t. Now, what is the period here? The period is all this. So t is 8 in this case. And that means that omega, which is 2 pi over t, would be pi over 4. Okay? All right. So what we need to do now, this should be the same height, okay? So what we need to do, and it should be the same height all over, of course, but just my drawing skills, Let's begin computing the bn's that we know have to be 0, because again, this is an even function. They cannot have sine components that are odd. Let's see. Bn, it's equal, in this case, to 2 over t, so 2 over 8, which is the value of t in this case. And then we get the integral from, we picked, what t0 do we get here? Well, conveniently we can pick t0 equals -4, and that's the integral from -4 to 4. So -4 plus 8, which is the period 4, it's one full period. You just need to pick one full period, okay? And this is dt, and this is capital G of t, right? We're doing this one. And the sine of n omega is pi over 4 in this case. So n pi over 4 t. Now, wonderful thing to realize. The sine is an odd function. G of t is an even function. You see, it's even. On both sides, it's equal, the function. So, the product of an even function and an odd function, the whole thing is odd. And the integral of an odd function over a symmetric interval is 0. Okay? So, as expected, bn is 0. We can write it down already. Has to be, because this is going to give us the cosine expansion. Cannot contain any sines. All right. Because of parity, you can do it if you want by parts and substituting, dividing this into intervals, one here and one here. This would be minus t, this plus t, and check that that's the case. But certainly you don't need to, because it's the integral of an odd function over a symmetric interval. Okay? Wonderful. Now, let's compute a0 and then an. So, a0 we can do here. A0 is 2 over 8, let's write it like that, integral from -4 to 4 of g of t times the cosine of 0, so dt, okay? Integral minus 4 to 4 of gt dt. Now, the nice thing about this is that g of t is an even function, and because it's even, the integral, which is the area under all this, is just twice the area under one semi-integral. So what we get is 1 over 4 from the 2 over 8 times 2, the integral from 0 to 4, g of t. Now g of t, I just write t, which is the value of the function here, okay? T times nothing, because the cosine is the cosine of 0, dt. This integral is easy, so I get 1 over 2 from this factor, then 1 over 2 from the integral, and then t squared evaluated from 0 to 4, and that thing is, again, 16 divided by 4, which is 4. So A0 is 4. Okay. Nice. All right, let's compute the AN. So the AN, it's equal to 2 over 8 integral from minus 4 to 4 g of t cosine of, recall, omega is 2 pi over t, t is 8, so omega is pi over 4, n pi over 4 from here, n pi over 4 times t dt. Now, thing that we realize, the cos is an even function, g of t is an even function, is the even extension. The product of the two is an even function. So I can write this as 1 over 4 from this, twice the integral from 0 to 4 of t cosine n pi over 8 t dt. Notice that I can write t here because I'm doing only 0 to 4. The function g of t is not t. The function g of t is only t from 0 to 4, but it's minus t from minus 4 to 0. And it's minus t plus 4 from 4 to 8. Certainly, at every different interval in here, the function is a different one, it's a piecewise function. But it's exactly t from 0 to 4, it's designed to be exactly t from 0 to 4, all right? And the reason that I can do that is because I'm integrating from minus 4 to 4, but the function is even, is this times a cosine, which is even, so the area under the function on both sides is the same, so I can write as twice the integral over the half integral, all right? Now, this is an integral that you do by parts, and I'll write the results by parts, so you get 1/2 from this, and the result of the integral by parts, if you do it just as it comes, is 16, and then denominator, and then minus 1 plus cosine of n pi plus n pi sine of n pi divided by n squared pi squared. All right, that's what you get by parts. Now, technically, that would be AN, and that would be correct. But you need to simplify a lot, and this is one of those cases that you need to work for the simplification. And second, let's do as an exercise. I mean, you don't really have to do it always because you compute A0 on its own. But let's see if we can get A0 as the limit when n goes to 0 from this. Let's compute what the limit when n goes to 0 of AN is. Let's take the factor. There's a factor 8 in the denominator and a factor pi over 2, pi squared, sorry, in the denominator. And then we get the limit when n goes to 0 of n squared in the denominator, and in the numerator we get minus 1 plus cosine of n pi plus n pi sine n pi. Right. Now, this limit is an indetermination. If you just substitute n, you get minus 1 plus the cosine of 0, which is 1, 0, plus 0, 0, divided by 0, indetermination. You can do L'Hopital if you want. I'll do Taylor expansion, remembering that the cosine of x is 1 minus x squared divided by 2, plus other things that I don't need. And the sine of x is equal to x. If I do that here, this thing is 8 divided by pi squared. And then I get the limit when n goes to 0 of n squared, still here, and I get minus 1 plus 1, that's going to cancel, minus n squared pi squared divided by 2 from the cosine from this term. The x is n pi. Now plus n pi multiplying the sine, which is n pi as well, n pi. So this thing is n squared pi squared. All right, now this cancels this, n pi squared minus n pi squared divided by 2, these two things together is n pi squared divided by 2 positive. Okay, again, the positive one minus half of it, so it's just half of it. Alright, so the result is 8 divided by pi over square, limit when n goes to 0 of, let's just write the numerator is n squared pi squared divided by 2 divided by n squared. The n squared cancels, the pi squared cancels, the 2 cancels the 8, the limit is the limit of 1, so what I get is 4, as expected. So it's true that I get a0 from this. Alright? This is just a sanity check. You usually don't need to do it, but it's good that you get used to doing limits. Maybe you want to do it with L'Hopital. Go ahead and do it with L'Hopital. I think it's much faster with table expansion. Alright, let's erase this. And once erased, we need, going back to our problem, to simplify this. How can I simplify? Well, remember, the cosine of n pi for integer n, it's equal, if I draw it, right? Cosine of 0 is 1, cosine of pi is minus 1, cosine of 2 pi, 1, cosine of 3 pi, minus 1. This thing is minus 1 to the n. And the sine of n pi is 0. Alright? So, we can simplify this, and this thing is equal to 8 divided by pi squared n squared, or n squared pi squared, I don't care. And I get this thing is minus 1 to the n. So this is minus 1 to the n minus 1, and then this is 0. Alright, so that's the coefficient. Now, this is one of those coefficients that can be simplified again, because we know that now an is equal to, now when n is even, this is 1 minus 1, which is 0. When n is odd, well, when n is even, this is 0 for n even, and it's going to be, when n is odd, this is minus 1, minus 1, minus 2. So it's minus 16 divided by n squared pi squared for n odd. Alright? Okay, so now we have to write the series, and it's important that the series can be simplified. So we have two options. So maybe I'll write the two of them so we see it. Okay? For sure, it would be correct, but not full marks correct, if you were to write, oh sure, the series would be, the solution would be that g of t is equal to a0 divided by 2, so 2, all right? And then I write plus 8 over n squared pi squared, I'm just copying the coefficient, sum, this is square, n equals 1 to infinity, of, and I write an, which is this times minus 1 to the n minus 1, cosine of n pi, not n, yeah, n pi over 4t, all right? And that is technically correct. It's not, I just copied the coefficient and used the formula, b is equal to 0. Technically correct, but not full marks correct. Why? Because I have here a sum over half of the terms are 0. I want to simplify it more, okay? So, what I do instead is pick only the odd ones in the sum, okay? To pick only the odd ones, I do the change for n going to 2n minus 1. That only picks the odd ones, an's odd ones. So that means that the odd an's are going to be a sub n equals to, well, n, if you want 2n minus 1, is going to be equal to minus 16, 2n minus 1 square pi square. You see, when n, what happens here when n is 1? When n is 1, right, when n is 1, I get a1 on the left equals minus 16 divided by pi squared, right? When n is 3 here, I get a3 equals minus 16 divided by 9 pi squared, right? Let's see what I get here. When n is 1, I get on the left a1, and on the right When n is 1, you say I get a1. And on the right, I get minus 16 divided by 2 minus 1 is 1. Square is 1. Pi squared. Oh, it coincides. Nice. What happens when n is 2? When n is 2, on the left, I get a3. You see? a3. 2n is 4. Minus 1 is 3. And on the right, I get minus 16. And then I get 3. 2n is 4 minus 1, which is 3 squared, which is 9 pi squared. So it coincides. You see, it's the same thing. I did nothing. All right. So if we clean this up, just to show you that it's the same. Okay. Now, that means that I can write my sum as follows. G of t is a0 over 2, and then plus sum n equals 1 to infinity. Now, I don't want to write the even ones, so I'm going to write only the odd ones. That's going to be a to n minus 1. That's only the odd ones. Cosine of 2n minus 1, only the odd ones, is a 1, times t. Remember, I substituted n by 2n minus 1. That's only taking the odd ones here. Every time I see an n, I write a 2n minus 1. All right? If it were only the even ones, it would be 2n. With minus 1 is the odd ones. Okay? And now I substitute, and I get that the final result is g of t, just to be able to box it. Is a0 is 4, so this is 2. 4 over 2 is 2. Plus, I take the constant factors out, so minus 16 divided by pi squared. And then sum n equals 1 to infinity of a to n minus 1. I write a 2n minus 1 when I see an n. So it's 1 over 2n minus 1. Okay? Squared. That's the n squared. The pi squared is out and 16 is out. And then finally, the cosine of, and then I have the cosine of 2n minus 1. 2n minus 1. Omega is pi over 4 times pi divided by 4. T. This is a 2. I hope that is understandable. All right. And this is the final result. This is the even extension. This is the cosine Fourier representation of f of t equals t in t from 0 to 4. All right. I hope this is clear. This is the only difficulty that I see here. It's identifying the minus 1 to be n properly, identifying when it's 0 and when it's not for values of an even or odd, and be able to change variables to adapt the series. But with a little bit of practice, this is easy. So I hope that that's clear. Again, I can repeat just for the sake of it. If you have a sum over some f sub n equals 1 to infinity, you can always decompose it in the sum over the evens, which is the sum n equals 1 to infinity f to n, plus the sum n equals 1 to infinity over the odd values of n, which is f to n minus 1. And in this case, the even ones are 0, we only get the odd ones. That's what I get. All right, let's see finally the sine Fourier series, which goes with the odd extension. So now we're going to compute the odd extension that will give us the Fourier series sine representation. Same as we knew before, the odd extension, if I wanted, I don't have to write the cosine terms because I know it's going to be odd. And an odd function cannot have even components. It needs to have odd components. It all needs to be sines. Okay? So I know that the ANs are going to be 0. But let's not assume it from the beginning. Let's compute everything, which is the safest. It's also a sanity check to see that we're doing things right. Okay, let's first do the odd extension. So the function from 0 to 4 is the same, is f of t equals t. So it's this one. And now we need to extend it. And we need to do the odd extension. The odd extension has to be on the other side, the same function, but in negative values. That's very easy. Just continue. T is an odd function. So that's an easy one. And then it would be like this, and it would be like that, and so on and so forth. That's the odd extension. Very simple in this case. All right, let's compute the different coefficients. That's easy. Let's compute A0 to begin with. A0, no, first, what's the period? The period is 8 as well. This from here to here. T is 8, which means that omega, which is equal to pi over t, it's again pi over 4, same as for the even extension. Now A0, then, it's 8 over 2. Sorry, 2 over 8, my bad. It's 2 over 8. And then we have the integral of f of t, h of t, this is h of t. So h of t dt, and then we pick one interval. Why don't we pick from -4 to 4? -4 to 4. But that one is easy because h of t is an odd function. This is the odd extension, right? So in a symmetric interval, an odd function, the integral is 0. So it's 0 from the beginning. Nice enough. We knew already has to be. There's no cosine terms here. All right, let's do an. An, when n is larger than 0, that thing is 2 over, well, that's actually for all of them. Anyway, whatever. An is equal to 2 over 8. And now we have the integral from -4 to 4 of h of t, the cosine of n pi over 4 times t dt. And then same as before, this thing is an odd function, this thing is an even function, it's a cosine, so the product of the two is odd. An integral of an odd function in a symmetric interval is 0. I don't need to do it again. 0 over 8, as expected. So an equals 0 for all n. Wonderful. Now let's compute the b. So bn, it's equal to 2 over 8, integral from -4 to 4, h of t, sine of n pi over 4 t dt. Now, we had an odd function times an odd function, odd times odd, it's even. So it's an even function, I think. That means that I can do 1 over 4, which is the 2 over 8, twice the integral from 0 to 4 of t sine n pi over 4 dt. All right, so this is an integral that you can do by parts. I'm not going to give you this kind of result, just do it by parts, there's no extra complications. It becomes -8 divided by n pi minus 1 to the n. The minus 1 to the n again comes from the cosine of n pi. When you get the cosine of n pi, that's minus 1 to the n. Now, one thing you can do is you can put the sign in here. This is the same as 8 n pi minus 1 to the n plus 1. It's having another minus 1 in the exponent here. All right. Now we can write the series finally, and we get h of t. This one is easy. There's no a0, there's no a, so directly we write the an terms, the bn terms. So the constants I write out, 8 over pi, and then this is the sum of minus 1 n plus 1 divided by n sine of n pi over 4 t, and that's the result. Just directly substituting from here. All right, so this thing is the sine Fourier, capital F. Representation of f of t equals t in the interval 0, 4. All right, let's put them all together to recap. So we have these three representations for the function f of t equals t. Capital F of t, it's plotted here in black. You see it's this one, this one, this one, this one, this one. G of t is the cosine representation, the even extension is the one in blue. It's this one, this one. And in red we have the odd representation, which is this one, this one, this one. And you can see that the three of them coincide in the interval from 0 to 4 and coincide with f of t. So f of t, in the interval, so if 0 less or equal than t than 4, less than t than 4, then we get that small f of t, it's equal to capital F of t, it's equal to capital G of t, it's equal to capital H of t. So these are different but valid coincident Fourier series in that interval. This is the full range expansion or representation. This is the even expansion. This is the odd expansion. Also call this one the cosine representation, or here this one the sine representation. And you can add the word Fourier in all of them. This is the full range Fourier expansion, the full range Fourier representation, the even Fourier expansion, the Fourier cosine representation, the Fourier cosine expansion even. All those things you can use combined, they're used everywhere with the different names, but hopefully now you can distinguish all of them. Alright, so in the next video, we're going to talk about the existence of the Fourier series, just a tiny bit. So under what conditions the sum exists. Remember that Fourier said when it exists. I'm going to tell you just a tiny bit because the math of that is a little bit more beyond the course level. And then after that, we're going to learn how to sum. We're going to learn addition and subtraction. Something that goes back to your first dates in school when you were kids, but now we're going to do it with Fourier series. And you see how helpful it is to take Fourier series to do sums. All right, but that will be in the next video. See you then. Bye-bye.